me just get the camera to rotate. Come on. Right. Oh dear. Right. So I was doing a lot of thinking about why my device speeds up when I put the shielding on the outside, and I'll try to explain it. I'm trying to find a decent pen here because that one's not so good. Let's see if this one's any good. Right, so we have a directional flow of magnetic fields as obviously the stator magnets, here, there, and they're not moving obviously, and the actual coil, which is wrapped around across these the core material. Obviously I'm using the older picture, so I was trying to work out what's going on, and I think I figured it out. So I want to show you what's going on. So when we put the steel, the nanocrystalline shielding material on the outside, paper's moving around now. When we put the nanocrystalline, and I kind of arced it a bit like that, but it doesn't have to be, and it can also actually be, it can actually go all the way around like that, because I've also tried that as well, where it goes all the way around. And the simplest way of explaining this is, what's going on is, so we've got these loops here, but they actually conduct, so the magnetism, that is. So the magnets are obviously not moving, right? So we have an energized field of magnetism which is actuated by the cores as the rotor is traveling in this direction. So the rotor is turning in this direction. So what's happening is, as these the core material enters between the magnet here, we'll just put south, so let's say that's south and that one's north, right? What's going on is that the field is being pulsed, the south field is being pulsed through this core material and obviously through the coil as well, and the flow is basically in the opposite direction. So the rotational effect is actually in the opposite direction, which is causing acceleration, which is why it's actually speed. You don't want to put this material on the outside. So it's really interesting, because what we've got going on here is there's multiple things happening, because what we have is angle of attack, which is in a triangular shape. So the magnetic field is basically in a kind of a V shape, right? Because as this is moving, imagine that point there is attached to this core material, and as it's moving, this triangle basically reverses. So when this core material is down here, the triangle shape of attack is in that direction, right? So we have like two triangles basically, effectively, and the field is basically being pushed, and it's flipping over to the other side, and the field is traveling through this core material that's on the outside, and the directional flow, I believe, is being reversed, so that what's happening is, as this rotor is moving in this direction, as I showed you with the arrow there, which I've done scribbled over the top of, we have a field travelling in the opposite direction down here, right? This is what I'm theorising on anyway. Or I might have that reversed, but whatever's going on, it's pushing the rotor forwards more. So obviously the north magnet down here is travelling through the core material here. This is the core material, and this is core material. So we have a circuit of magnetic field travelling all the way around here. But when the rotor is moving further out the way, what happens when these segments, when this segment is in the center here, when it's right in the middle as the rotor moves, that core is effectively shorting out this magnet and this magnet together, so the field collapses. So the field's present all the time except when it collapses the field. So when this core is over here, the field is basically short-circuited, so that it collapsed. It's very hard to figure this out, obviously, and it's just a theory, but it's obviously the reason why it's generating power, but it's simply because of the actuation of the field. It's obviously, you have to move things around to get power, don't you? So I mean, yeah, just some thoughts anyway. So it's not very clear. I know I'm still theorizing it and trying to figure it out, but whatever's going on, oh, it's the lensing effect. Yeah, it's the lensing effect that's doing it, not the actual magnetic field. It's the lensing effect. So when we have a lensing effect where the equal opposite reaction of the coil is induced on this piece of tin, well, just call it tin, which is nanocrystalline. I'm getting lost now. Anyway, just some thoughts. You tell me what you think anyway. Bye for now.